Do you know the reason for using Litz wires and twisted pair wires at frequencies like 10 kilohertz to 1 megahertz? The reason is it is because of the skin effect. So in this video we can check what skin effect actually means. Consider a conductor like this. If we are passing a direct current through this conductor, the entire area in this conductor will be equally carrying the current. The current will be distributed within the conductor uniformly. So I am taking the cross section of this conductor to show how the current distribution is inside the conductor. Here we can see that when the current is direct, the entire conductor is occupied with the current, or the current is uniformly distributed. But when an AC or alternating current is passing through this conductor, all the current will be concentrated on the outer layers, and the current concentration on the inner layer will be very less. As the current is mainly concentrated on the skin or outer surface of this conductor, this is known as skin effect. The parameter used to represent or specify the skin effect is skin depth. This is the skin depth. This actually measures the depth at which the current is reduced to 37% of the maximum value at the outer conductor. So we usually use this skin depth as a parameter to specify the skin effect. So this is the equation to calculate the skin depth, and it is del is equal to square root of rho by pi f0 mu r mu 0, where rho is the resistivity of the conductor, f is the frequency, and mu r is the relative permittivity, mu 0 is the free space permittivity. Here we can see that the skin depth is inversely proportional to the frequency. That means that as the frequency of this alternating current increases, the skin depth decreases. That means the current will be concentrating only on the outer layers as the frequency increase. It will not be occupying the uh, inner layer of the conductor.
Before going to the details, let's try to understand some basic concepts related to the skin effect. So if we have a conductor like this thing, and if the current in that conductor is varying, it will be producing an alternating magnetic field. The direction of the magnetic field produced by this current can be given by right hand grip rule. So if this is my right hand, and if I am aligning my thumb in the direction of the current, the rotation of all these fingers will give me the identification of the direction of the magnetic field. That is right hand thumb rule. Okay, so this is my right hand, but as the camera is flipped, it may looks left hand to you, but this is my right hand. So in first case, we can see that the current is in this direction. So if I wrap my fingers around the conductor, you can see the direction of the magnetic field. So in case of alternating current, the direction of the current will be changing. So we can see that with respect to the direction of the current, the direction of the magnetic field will also be changing. So that is given in these two pictures. Here you can see that when the direction of the current is in this direction, the magnetic field in, produced by the current is in this direction. When the direction of the current changes, the magnetic field direction also changes. That means that an alternating current produces a change in magnetic field. So when a change in magnetic field occurs, this conductors does not like these type of changes in magnetic field, so they wants to make sure that everything is like stable or constant. So this conductor will produce some induced current in such a way that they wants to make sure that nothing is changing. So this changing magnetic field produces an induced current, and when this induced current produces another magnetic field in such a way that they will oppose any changes in this original magnetic field. That is the process. So this one is known as Lenz's law. So Lenz's law states that the direction of the electric current induced in the conductor by changing magnetic field is such that the magnetic field produced by the induced current opposes the actual magnetic field produced in it. So we have to understand Lenz's law to understand the skin effect. Uh, just to understand the skin effect in metal, what I'm going to do is I'm going to split the conductor into tiny, small conducting strips like this. Here you can see that I have divided this conductor into tiny, small conductors, and I am going to consider one conductor from that. So this is the uh, one conductor from inside this conductor, and I have cut some portion of this conductor to show how this magnetic field is varying and how the induced current is produced inside that. So let's see, the current is passing in this direction through the conductor. Because of this current, as it is alternating current, it will produce the magnetic field. So using right hand grip rule, we can see the direction of the magnetic field. So here we can see that it will be coming out from this direction and it will be going out at this point. So in previous slide, we have seen that Lenz's law state that if the magnetic field is changing, it will produce the induced current, and induced current will produce an induced magnetic field to oppose this magnetic field. So we know that this will eventually produce an opposing magnetic field. So the third picture shows the direction of the opposing magnetic field, because we know that this is the produced magnetic field and the induced magnetic field has to oppose this magnetic field. So this is the direction of the induced magnetic field. So I have shown these red arrows to show the direction of the magnetic field. So it will be coming out from this point and eventually it will go out, go through the conductor at this point. So my actual aim is to find out the induced current direction. So I know that this is the magnetic field produced by the induced current. So using the right hand thumb rule again, I'm going to find out the induced current direction. So these are the magnetic field direction. So in fourth picture, you can see the magnetic field direction shown just by arrows. And I am going to put my thumb in the direction of the magnetic field. Here, this curl of these fingers will represent the induced current direction. So here we can see that the induced current at this point will be like this, and on the other direction, the induced current will be like this. So here we can see that at the mid of the conductor, the direction of the induced current is opposite to that of the actual current. Here you can see that this current direction is opposing to the actual current. But this ends, you can see the direction of the current is in same direction as that of the original current. So this means that the induced current is opposing the actual current in the midpoint and it is in the same direction at the ends. Because of this opposition, the skin effect in metal is occurring. So here I have considered only one metallic structure, one strip from this entire conductor. So these type of effect will be there in every conducting strip that we have considered. But we know that the surface current is mainly concentrating only on the outside. So let's see why it is so. Considering a small part from this entire conductor, we have made the conclusion that the induced current produced in the middle will be in opposing to that actual current, and at the ends, it will be supporting the actual current. So Our actual current conductor is made up of several such small conductors, but we have seen that there is no current inside the conductor as a whole. That means here there is no current, but only at the edges it is supporting the current. So let's see why it is so. So here is an exploded view of this conductor, considering several conductors. Here you can see that the middle conductor will be surrounded by several conductors, and the current in these surrounding conductors will have influence on the middle conductor. Because of this influence, or we can call it as the mutual inductance, the opposition produced by these middle conductors will be very high. When you consider the conductor on the edges, you can see that the influence on this conductor is only from one side, as there is no conductor on the other side. So the opposition produced by this conductor will be very less. That means that the opposing induced current produced by the middle conductors will be very high due to the mutual inductance from the surrounding conductors, and the surrounding conductors will be producing only less resistive current. That's why we are not getting any current inside the conductor, and we can see the current conduction is reduced onto the skin of the conductor. So here you can see that the opposition produced in the middle will be very high due to this mutual inductions, and the opposition produced at the skin of the conductor will be very less. So we can understand this better by considering a car, uh, lots of cars in a traffic analogy. Here you can see that these cars can be considered as inner conductors, and these cars can be considered as outer conductors. So here you can see that these inner conductors, if these inner conductors has to move, or it has to make some decision, it has to take consideration of the cars on this side and cars on other side. So it is like more restricted. And when you consider the cars on the edges, the resistance offered by this car will be very less, because this car has only influence from one side, as this side is free. So similarly, the inner conductor will produce more resistance to the actual current, and they will oppose the current inside the conductor. So it will be deprived of the current inside the conductor, and all the conductors will be concentrated on the skin of the conductor. That's why skin effect is happening. This slide shows the skin effect impact with frequency. So we know that this is the equation to calculate the skin depth. Skin depth is inversely proportional to the frequency. This means that as frequency increase, skin depth will decrease. So here you can see that at DC, the entire area of the conductor will be occupied by the current. But as the frequency increases, you can see that the effective area occupied by the current will be decreasing. So here you can see a table for the conductor copper, how the skin depth is varying with respect to frequency. Here you can see that at 500 megahertz, the skin depth is around 2.95 micrometer. But as the frequency increases, you can see the skin depth is effectively decreasing. So this means that even if you are using the thick conductor at high frequency, that conductor will not be occupied by the current. Only this fraction of the conductor will be occupied by the current. And there is one more parameter, resistance. This is the equation for the resistance. Here we can see that the resistance is inversely proportional to the area. So here we have seen that as the frequency increases, skin depth decreases. This means that effective area occupied by the current is decreasing here. that means that resistance will increase. So this means that with increase in frequency, skin depth decreases and the resistance will be increasing with frequency. So that's all regarding the skin effect. So we have discussed what is skin effect and why it is occurring and its impact with respect to the frequency. The next part of this video will be regarding the proximity effects in metal. And if you like this video, kindly like, comment, share, and subscribe. Thank you.